Alright, welcome back. I hope I've not jaded or offended any one of you. Um, Now I've not worked on this problem a little bit, but I'm thinking that if you've done it exactly the way I've told you to, then you should have gotten an error in your code. And that's totally fine. You've not done anything wrong. We're going to talk about this. So, you should have gotten an error saying that your matrix was singular and it can't find a solution. You're like, wait a second, I did everything right. I set this up. You double-checked your equations. It's okay. You did it right. Let's talk about why. Okay? Now, let's go back a bit and talk about Green's identities. Remember, if we've got some surface S, and we've got a flow outside of here, and that flow outside is governed by some velocity potential phi. Remember that in order to make the discretized boundary integral equation work, we had to introduce a fictitious inner potential, phi sub I. Okay? And we said that the doublet strength on our surface, mu, is equal to phi minus phi sub I. So mu represents a jump in potential as we're going from the inside to the outside. Okay? Now, in order to figure out what mu was on this surface, we set up some boundary conditions, and we said that on the surface of this, we want grad phi to be equal to, we want grad phi dotted with n to everywhere be 0. Okay? And based on that, we figured out what mu was. Well, let's think about what phi is on the surface. Phi on the surface is phi inner plus mu. Okay? And so what we've really said is I want grad mu plus phi inner dotted with n to be equal to 0. And you're like, all right. What does that have to do with the fact that my matrix is singular? Okay, well, let's talk about what does phi sub I have to be in this case. Well, if you'll remember, and we're going to have to go back to what we know about sources. Again, sources aren't here, but it's important that they're not here. The source strength on the surface, oh, come on, draw for me. The source strength on the surface is equal to the jump in the normal derivative. So partial phi partial n minus partial phi sub I partial n. And we can also write this as grad phi dotted with n minus grad phi inner dotted with n. Okay? Well, since we've said that we don't have sources, we want source strength to be 0, we then have that everywhere partial phi partial n is equal to partial phi sub I partial n. Okay? So because we've said that there aren't sources, we've now introduced this condition on the inner potential. And moreover, if you recall, we've set our boundary condition, grad phi dot n equals 0. Because of that boundary condition we've induced, well, this term here is just grad phi dot n is equal to 0. Well, then that means that this term here is also equal to 0. So by saying there aren't any sources, and by enforcing our zero normal flow boundary condition, we have said, whether we like it or not, partial phi inner partial n is equal to 0. Okay? Now I won't get into the exact specifics of the math here. If any of you are interested, come and talk to me. It's an interesting problem to work through. But I can say and I can prove this to you, maybe I'll do that in a separate video, that if I have this condition, as well as the condition that grad squared phi I is equal to 0, so if phi sub I is harmonic, if phi sub I satisfies Laplace's equation, then based on these two conditions, I can state definitively phi sub I is constant. Phi sub I is some constant value inside of this configuration. I know that. Okay, I can prove it mathematically. You can exploit this, and we will in the next video, to actually solve for your double strengths another way. But for now, we're just going to talk about why is my matrix equation singular. Well, if phi sub I is some constant, ask yourself, what is that constant? Have we at any point in this formulation specified what phi sub I should be? It's a constant, we can show that from the math, but do we know what that constant is? No, we don't. And that's the problem. Now, if we go back to what we had up here, remember I said that essentially the boundary condition that I'm enforcing is grad of mu plus phi sub I is dotted with n is equal to 0. And so, if I bring that down here, grad of mu plus phi sub I dotted with n is equal to 0. Well, if phi sub I is a constant, what's the gradient of a constant? That's just always 0. And so, no matter what phi sub I is, this equation is always satisfied. And so if I say phi sub I is 2, well, that's fine. It doesn't matter. If I say phi sub I is negative 12, it doesn't matter. If I say phi sub I is e to the square root of 2, it's fine. It doesn't matter. But the problem is that's going to have an effect on what the doublet strength is. Now we know that our outer potential decays to 0 at infinity. The way we've set up our influence coefficients, the way we've done things, as phi here goes out to infinity, it's going to go to 0. And so it doesn't have this arbitrary constant to it. And so, recalling that mu is equal to phi minus phi sub I, well, let's say that phi, our true solution, is 2, and phi sub I is 3, then that means that mu is negative 1. Okay? Alright, that's not fitting. Mu is negative 1. Okay? Well, but if phi is still 2, or again, we have no arbitrary constant, phi is fixed, but now for some reason our arbitrary constant phi sub I is negative 5, well then that implies that mu is equal to 7. So there's no unique solution to this. There's an infinite number of solutions that satisfies this equation right here, simply because there are an infinite number of inner potentials that satisfy our equation. Now, would you have ever, we would never have guessed that, you know, just applying our boundary conditions saying, oh, I've got n unknowns, I've got n equations, I'm good. This is why it's so important to understand the underlying math. This is why we spent that time going through Green's identities, the derivation of the boundary integral equation, is to be able to understand things like this. That's why you're taking a class like potential flow right now, so that you can understand this type of behavior. This kind of stuff you don't get as an undergrad. So, now that we know that, well, how do we deal with it? So there is hope. Thankfully, we have an infinite number of solutions and not no solutions. If your matrix A is singular, you can have either. You can have an infinite number of solutions, or you can have no solutions. In our case, we have an infinite number of solutions. So we just have to pick one. You can do that a few different ways. In your code, what you can go ahead and just use is you can use numpy.linalg.lstsq of A, B. And LSTSQ stands for least squares. And what that will do is it will pick the doublet strength vector that solves that equation with minimum magnitude. So the magnitude of that whole vector, it'll pick that minimum. Now if I'm remembering right, depending on your instantiation of Python, calling numpy.linalg.solve on this system, even though A is singular, may still give you an answer. And so go ahead and look at the two and compare them. See what the difference is between the two and see if you can figure out what exactly is going on. Anyway, that's why the Neumann formulation gives you a singular matrix. It's because it's not unique. And in the next video, we'll talk about a different way of formulating this problem that makes it unique. Okay? We'll see you next time.